Finding and verifying the inverse function. Hello everyone. Let's begin our lesson on finding and verifying the inverse function. To start, let's recall what we discussed in our previous subsections. We established that for a function, f mapping from set x to set y, to possess an inverse, it must be a bijective function. In other words, the function must be both one-to-one and onto. Now, once we have confirmed that a function is indeed invertible, the next logical step in our process is to determine the actual algebraic expression for that inverse function, which we denote as f inverse. To understand this conceptually, you can think of the inverse function as a mechanism that essentially reverses the mapping of the original function. For example, if the original function, f, takes an input x and maps it to an output, y, then the inverse function, f inverse, takes that output y and maps it back to the original input, x. In the following slides, I will guide you through the systematic procedure to find this expression and show you how to verify that your result is mathematically correct. Procedural guide to finding the inverse function. Now that we have established the theoretical requirements for a function to be invertible, let us move on to the practical application. To find the algebraic expression for the inverse of a function, f of x, we follow a systematic four-step procedure. First, in step 1, we set the function equal to y in practice. This means you replace the function notation, f of x, with the variable y. We do this because it is much simpler to manipulate a single variable algebraically than it is to work with function notation. So, your equation will start as y equals f of x. Once that is done, we proceed to step 2, which is to solve the equation for x. Your objective here is to rearrange the equation to isolate x on one side, effectively expressing x as a function of y. To achieve this, you will use inverse operations. For example, if the original function uses addition, you will apply subtraction. If it uses multiplication, you will apply division. By the end of this step, you should have an expression in the form of x equals g of y. Now that x is isolated, we move to step 3, defining the inverse function. At this stage, you simply replace the variable x with the formal notation for the inverse function, which is f inverse of y. This provides you with the official expression for the inverse, written as f inverse of y equals g of y. Finally, in step 4, we address the final notation, which is often optional but highly recommended. Since the original function was expressed in terms of x, it is standard mathematical practice to replace the variable y in the inverse function back with x to maintain consistency. This results in the final form, f inverse of x equals g of x. Now, finding the expression is a critical first step, but it is not the end of the process. In the next slide, I will explain how to verify that the inverse function you have just calculated is mathematically correct. Verifying the inverse function. Now that we have covered the procedural steps to find an inverse function, we move on to a critical part of the process, verification. It is important to understand that finding the algebraic expression is only half the work. Verification is what ensures that your result is mathematically accurate. In formal terms, a function g is the inverse of a function f if and only if the composition of these two functions results in the identity function. To verify this, you must check two specific conditions. First, the composition of f inverse and f of x must equal x for all values of x in the domain of f. This essentially means that if you apply the function and then apply its inverse, you should return to the original input. Second, you must check the reverse order. The composition of f and f inverse of y must equal y for all values of y in the domain of f inverse. This confirms that the inverse relationship holds true regardless of which function is applied first. If and only if both of these conditions are satisfied, the inverse is officially verified. We will see exactly how to apply these checks in the upcoming examples, starting with a real-world temperature conversion scenario. Real-world example, temperature conversion. Now that we have covered the theoretical framework and the step-by-step procedure for finding an inverse, let us apply these concepts to a practical, real-world scenario: the conversion between Celsius and Fahrenheit. In this scenario, we are given a function that converts Celsius to Fahrenheit. This is expressed as f of c equals 9/5 c plus 32. Our goal here is to find the inverse function, which would allow us to convert Fahrenheit back into Celsius, and then verify that our result is mathematically sound. Let us follow the procedural guide we established in the previous slide. First, in step 1, we set the function equal to a variable. In this case, we will use f to represent Fahrenheit, so we write f equals 9/5 c plus 32. Moving to step 2, we need to solve for the independent variable, which is c. To isolate c, we first perform the inverse operation of addition by subtracting 32 from both sides of the equation. This gives us f minus 32 equals 9/5 c. Next, to completely isolate c, we multiply both sides by the reciprocal of 9/5, which is 5/9. This results in c equals 5/9 times the quantity f minus 32. Now we reach step 3, where we formally define the inverse function. We can denote this as f inverse of f equals 5/9 times the quantity f minus 32. However, as we discussed in the slide on verification, finding the expression is only half the work. We must ensure that the composition of the function and its inverse results in the identity function. First, let us check the composition of f inverse and f of c. We substitute the original function into the inverse formula. This gives us f inverse of the quantity 9/5 c plus 32. When we plug this into our inverse expression, it becomes 5/9 times the quantity 9/5 c plus 32 minus 32. The positive and negative 32s cancel each other out, leaving us with 5/9 times 9/5 c. Since these fractions are reciprocals, they cancel out, leaving us with just c. This confirms the first part of our verification. Second, we must check the composition of f and f inverse of f. We substitute the inverse expression into the original function. This gives us f of the quantity 5/9 times the quantity f minus 32. Substituting this into the original formula, we get 9/5 times the quantity 5/9 times the quantity f minus 32 plus 32. Again, the 9/5 and 5/9 cancel each other out, leaving us with the quantity f minus 32 plus 32. The 32s cancel out, leaving us with just f. Since both compositions return the original input, the inverse is fully verified. In the next slide, we will apply this same logic to a more abstract algebraic problem. Algebraic example. Now that we have explored a real-world application with temperature conversion, let us apply the same systematic approach to a purely algebraic problem to further solidify your understanding. Our objective for this example is to find the inverse of the function f of x equals 2x minus 3, all divided by 4, and then verify that our result is correct. Following the procedural guide we established in the previous slides, we begin with step 1. Setting the function equal to y, this gives us the equation y equals 2x minus 3 over 4. Moving to step 2, we need to solve for x to isolate it on one side of the equation. We do this by applying inverse operations. First, we multiply both sides by 4 to eliminate the fraction, which results in 4y equals 2x minus 3. Next, we add 3 to both sides to move the constant, giving us 4y plus 3 equals 2x. Finally, we divide both sides by 2, which leaves us with x equals 4y plus 3, all divided by 2. Now we proceed to step 3, where we define the inverse function. We replace x with the notation f inverse of y, so we have f inverse of y equals 4y plus 3 over 2. As we noted in our guide, it is common practice to express the final answer in terms of x for consistency, so we can also write this as f inverse of x equals 4x plus 3 over 2. Finding the expression is only half the work. We must now verify it to ensure no algebraic errors were made. We do this by checking if the composition of the two functions results in the identity function. First, let us check the composition of f inverse of f of x. We substitute the original function into the inverse function. This gives us 4 times the quantity 2x minus 3 over 4, plus 3, all divided by 2. When we multiply by 4, the fraction is cleared, leaving us with 2x minus 3 plus 3, all over 2. The negative 3 and positive 3 cancel each other out, leaving us with 2x over 2, which simplifies perfectly to x. Next, we verify the reverse composition. F of f inverse of y, we substitute the inverse expression into the original function. This gives us 2 times the quantity 4y plus 3 over 2 minus 3, all divided by 4. The 2 in the numerator and denominator cancel out, leaving us with 4y plus 3 minus 3, all over 4. Again, the constants cancel, leaving us with 4y over 4, which simplifies to y. Since both compositions return the original input, we have mathematically verified that our inverse function is correct. In the next slide, we will discuss some common mistakes to avoid so you can navigate these problems with confidence. Common mistakes. Now that we have walked through the procedural steps and worked through a few examples, let us address some common pitfalls to ensure you avoid them in your assignments and exams. First, it is crucial not to confuse the inverse function with a reciprocal. A very frequent error is assuming that f inverse of x is equal to 1 divided by f of x. Please remember that in function notation, the superscript minus 1 represents the inverse mapping, the process of reversing the function, and not the multiplicative inverse or the reciprocal. Secondly, be mindful of algebraic errors during the isolation process. As we saw in our previous procedural guide and the algebraic example, rearranging equations to solve for x can be tricky, especially when dealing with fractions or negative signs. To avoid these mistakes, always ensure you perform the exact same inverse operation on both sides of the equation to maintain mathematical balance. Thirdly, avoid the temptation to skip the verification step. While it may seem time-consuming, as we discussed in the slide on verification, this is the only definitive way to ensure that no algebraic slips occurred while you were isolating the variable. If the composition of the two functions does not result in the identity function, you know immediately that you need to recheck your algebra. Finally, do not ignore the relationship between the domain and the range. It is easy to forget that the domain of the original function becomes the range of the inverse function, and conversely, the range of the original function becomes the domain of the inverse. Keeping this in mind is essential for the function to remain bijective, as we established at the beginning of this lesson. Key takeaways. To wrap up our lesson, let's review the key takeaways to ensure you have a solid grasp of the material we've covered. First, let's revisit the primary goal. The inverse function, denoted as f inverse, is designed to reverse the action of the original function. Think of it as an undo operation that brings you back to your starting value. Next, let's summarize the method we used in our previous examples. To find the inverse, you simply replace the function notation f of x with the variable y, solve the resulting equation to isolate x, and then rename that final expression as f inverse. Regarding verification, as we demonstrated with the temperature conversion and the algebraic problem, finding the expression isn't enough. You must ensure that the composition of the function and its inverse yields the identity function. This means that f of f inverse of x must equal x, and likewise, f inverse of f of x must also equal x. Finally, always remember the fundamental requirement we discussed at the very beginning of this session. A function can only possess an inverse if it is bijective, which means it must be both one-to-one and onto. Keep these points in mind, and you will be well equipped to handle any inverse function problem.